From first unit, we discussed different contributions to the magnetic moment. Contributions to the magnetic moment. Like we have orbital magnetic moment, then spin magnetic moment, then there was the vector atom model which gave us total angular momentum. Now in this chapter, in the second unit, we will discuss interactions between different components of magnetic moment, and these interactions, they will act as a perturbations. These will act as a perturbations when we calculate the energy corrections. Accordingly, we will calculate the energy corrections. And in corrections to what? If you remember that from Bohr's model of hydrogen atom, we discussed spectra, hydrogen spectra, and we saw that there's a line spectra which corresponds to different n, and then different n, different l. Then we saw that corresponding to n, there is l, then we have ml, ms, and then mj. These are the different quantum states. But from Bohr's theory, we do not have these all. We only have n and l. So the line spectra was explained on the basis of these two quantum numbers that corresponding to each value of L and N. We can have a line in the spectra, we can have a feature of the spectra, but it was not only that. There were more features which were there in the atomic spectra of hydrogen atom. And when it was observed that using high resolution spectrometers, using high resolution spectrometers, it was observed that all spectral lines all spectral lines starting from s level, that is s orbit, with L equal to 0, with L equal to 0, since it's the s level and L will be 0 for s, it consists of two narrowly spaced components, or which was called as doublet. It was called as doublet actually. But what about for L greater than 0? there were more features. For example, L equal to 1, we have P, and there was a triplet. Okay, so there were more features, and for even higher L, more components were there, more complex structure was found. Since these were observed only with the help of high resolution spectrometers, so and they were very fine, so this was called as a fine structure. This was called as a fine structure of hydrogen spectrum. So these closely spaced lines which were observed in the hydrogen spectrum, it was named as a fine structure. And several experiments were done. Then spin cam, actually the spin magnetic moment or the spin quantum number was one of the important factor in explaining the origin of those fine structures. So the origin of fine structure in hydrogen spectra was revealed with the discovery of spin. Spin was the important factor in explaining the origin of those fine structure, that is doublets in case of S is equal to where this L is equal to 0 for S orbit. And important point is that those fine structure are doublets or fine structure cannot be explained by Schrodinger equation. Schrodinger equation was so doublets are the fine structures of this hydrogen spectrum. It was not able to be explained by using Schrodinger equation, because if you see the Schrodinger equation, you will only find L, not S, or you will not find an interaction between L and S, L dot S. So Schrodinger equation was not able to explain the fine structure of this hydrogen atom or the spectra of the hydrogen atom. Now, what exactly is fine structure actually, or what exactly is spin orbit interaction? Spin orbit interaction is one of the origins of the fine structure. Just remember it, that spin orbit interaction is one of the origins of the fine structure, one of the reason of the origin for the existence of fine structure. So what is actually that spin orbit interaction? We know that in an atom we have a frame of reference. If we have a nucleus, this is the nucleus, these are the electronic orbits here, and here electron, this is the nucleus, this is radius r, then this, it is a spin magnetic moment which is perpendicular to this. I can write mu as z here if it is like that. Then if this is z e plus, but it is a proton here and nucleus, this is the orbital angular momentum, this is the magnetic moment of the electron, this nucleus, sorry, not the orbital, and this is the radius vector here. We here what we observe is that we observe that nucleus is at rest. So the nucleus is at rest when we see from electrons frame of reference. Sorry, when we see it, nucleus is at rest and electrons are moving. Nucleus is at, electrons are moving when observed from nuclear frame of reference. So that means the electron has a motion with respect to the nucleus, but when we see it from the nucleus frame of reference. But what happens when you observe nucleus from electrons frame of reference? That means when we observe it from electrons frame of reference, the frame of reference will change. And in this case, electron will be treated at rest and nucleus will be moving with respect to electron. So nucleus has an orbital motion around the electron. Okay, just this is an important point you have to understand the spin orbit interaction. So in first case, we know that electron is moving about in nucleus. Yeah. So in first case, what we understand is that electron is at rest. This nucleus is at rest and electron is moving around it. But when you see it from the electron's point of view, that means when electron will be considered, that means if an electron, if you see with the electron, you will observe that nucleus is moving about the electron because you are just changing the frame of reference. Orbital electron was in the electron was having an orbital motion, then it was having an orbital angular momentum. So in the same sense, when the nucleus will be moving with respect to the electron, it will have its magnetic field, and this will be the internal magnetic field. So what is actually the spin orbit interaction? It is an interaction between the orbital spin magnetic moment, that is mu s, spin magnetic moment, and orbital magnetic moment of nuclear field. Nucleus, that is a magnetic field which is because of the nucleus. That magnetic field will interact with the spin magnetic moment of this electron, and it is called as spin orbit interaction in this case. And this magnetic field, which arises because of the orbital motion of those nucleus, orbital motion of that nucleus, it is the internal magnetic field of an atom. And there's a nuclear field, so that nuclear field and the spin magnetic moment, they will interact each other. Now if you know that since this nucleus has a positive charge, so it has electric field associated with it, and that electric field, if we write by E, electron is moving in this electric field as well. So E, we know that it is gradient of V, del V. So this is what we know actually from earlier class. Potential, that is gradient of a potential function VR from electrodynamics. So it is R by R. I can write dV by dr, and this V is a function of R. But what I have used is actually gradient of R is equal to this vector R by R. Actually, simply it is a vector, not gradient. This is not, the gradient is not needed here. So this is simply a vector, and we can write it vector R divided by mod of R. This is a unit vector actually. This, which gives the direction, radial direction of E. Now we have electric component, we have a magnetic field, that is a spin magnetic moment, an electric field of that new proton as well. Then we have the magnetic energy, which is stored in this due to this interaction, due to the interaction of the electron between these two fields. So there's a magnetic energy, and how it is written? So you have done this. B is equal to 1 by c square E cross V. Or if you put up the value of this E from this equation here, so B will be equal to 1 by c square into R into d by dr of V of R, and the cross product will remain there. This R is from here, this, and this V is from here. All the other terms are constant actually, they are assumed to be constant. We are putting up the values of E here, so this comes in. Now orbital angular momentum of the electron will be, because it has a motion, it is moving when we are treating it from the nucleus frame of reference, so that will be equal to mr into V. If we make the substitutions in this case here, R cross V, this R cross V in this case, in equation, above equation, what we can write? We can write B is equal to 1 by mc square, because m is in the numerator, that will go for R, this L, and since we don't have m there, so we will divide by m, this m, because there is no m in the numerator, so we will do it just like m by m here. So it went m r into V divided by this m, so that m is here, and this is 1 by R d by dr of V of R into L, because we have introduced now the orbital component of the electron as well. Okay, interaction is because of the nuclear field, but there is a orbital magnetic moment as well. Now the electron and its spin magnetic moment mu s, they can assume different orientations. We already know this. Orientations in the internal magnetic field B of the atom, which arises because that of nuclear motion, and that energy, the energy stored, that we already have discussed, that it will different for different orientations actually. And if you remember that the magnetic potential energy of an electron, because electron is now a dipole actually, and it is in the internal magnetic field which will be external for it. The origin is internal, but this magnetic field will be treated like it is acting on an electron. So just like we have treated the electron in an external magnetic field, dipole, magnetic dipole in an external magnetic field. So in the same sense, electron is here, the magnetic field is internal, that is source is internal, but it will act on the electron, and electron will be treated in the external that field. So there is an interaction when, so that we will write delta E, which is the energy, or the, because of the orbital and spin interaction is Ls. This is a potential energy. It is minus mu s dot B. We already know that U is equal to us dot B. That's the energy, magnetic energy. Now we know that mu s is equal to minus gs E by 2m into s. Okay, and for spin the gs is equal to 2. So using these equations, these expressions in the above equation, this expression in here, we can write delta ELS will be equal to E by m s dot B, this B here. Now B we have already calculated. This is the B equation. This is the mu equation. So S is there, B will be there. So I will write the equation using the value of B from above. I can write delta ELS will be equal to E by m square C square 1 by R d by dr of V of R, and it is S dot L. This is S, this is L. Since it is a dot product here, so these two vectors will have a dot product. This. And this is the energy actually in the frame of reference in which the electron is at rest. Just remember that. Energy in the frame of reference
ये स्टेट पॉसिबल है क्योंकि आज तक हमने सुना था कि इलेक्ट्रॉन इज मूविंग अराउंड द न्यूक्लियस.
Yeah, it is just the change of the frame of reference. You're changing the frame of reference. It is not exactly, but
It is
what you,
relative.
it is relative actually. So it can be seen as like if I am here standing and I am seeing a moving bus, so with respect to me, bus is moving. But a person which is in the bus, he will see moving me because he's at the rest frame of
Yes.
reference inside the bus. Okay, it's just like that. And since this is a relative, you have heard of relativistic transformations. To the normal frame of reference, from relative frame to normal frame. One is relative frame and one is normal frame. So when you do the transformation, this is called, then what we do actually, the energy is reduced by a factor of 2. So the relativistic transformation means that the transformation of a relative frame to normal frame of reference actually. Because we are all treating it with non-relativistic. We are not going into the relativistic components. So what we are seeing, we will convert this whole problem into a normal frame of reference. And if you have done the relativistic transformations, then the energy factor is reduced by a factor of 2. And this is called a Thomas precision actually. Due to the Thomas precision, this L and S, it will be E by m square c square. I will reduce it by 2. So there will be a factor divided by 2 because of the transformation. I will send you this article related to this S dot L. Now, we will, this is the one of the important results. Now we will need this result to move further ahead. We don't need to do any other used any other concepts. Now we know that J is equal to L plus S. I will just evaluate this term S dot L. Spin and orbital interactions. So L plus S. Now, if you take J dot J, it is L plus S dot L plus S. These are all vectors. I can write it as simply, we have already I think done it, and it is this L dot L plus S dot S plus 2i's S dot L, because it is scalar product. So we can write S dot L is equal to L dot S.
Yes.
L dot S. The scalar product. So it is. Now, what we need here L dot S dot L. So you can derive it from here. It gives us S dot L will be equal to L plus S. Sorry, not this. S dot L is equal to, you can write S dot L is equal to 1 by 2 J dot J minus L dot L minus S dot S. So this is simplest equation, and you can then, it is one, since it's a dot product, so it is only J square minus L square minus S square. And using the values of J equal to J into under root of 1 plus J plus 1. So we can write 1 by 2 J into J plus 1 minus L into L plus 1 minus S into S plus 1. There's H cut square. So this is H square by 4 pi square. Okay. Yes. Now we can use this value of S dot L here in the above equation, this equation here. Yes. What we get? We find that delta E L comma S is equal to E H square by 16 pi square, because 4 is here and 4 will be there. It's 2 and 2 is outside here. This 2, this 4, 8, 8 2s are 16. So it is 16 pi square, and there's m square c square, and in the bracket open, j plus 1 l plus 1 s into s plus 1, and there's a term from the potential term, that is 1 by r dv by dr. So this is the expression. This we will modify further. And if you see this term, this 1 by r, this all is actually, we know, we have already done. The term that's important is 1 by r. It seems that it is a constant, but it's not actually a constant, because the average value is calculated for this. 1 by r is not constant during the electron motion. Hence, we must take its average value over unperturbed motion. Unperturbed motion means that when there is no interaction actually at all. This 1 by r varies over whole orbit, and under the influence of this potential field, because of the nuclear motion, relative motion of the nucleus, this varies actually dv by dr. So it's not constant actually during electron motion. And then we take it as average value like this, or we can simply write 1 by d by dr of v this bar. So this is the average motion, average value of this function. And we can write then this is the general expression for spin orbit interaction. You can remember it, but you can further modify it. If we consider the one electron atom, if we consider one electron atom or like a hydrogen atom, then you must know how to calculate the average value, this 1 by r dv by dr. We must know it. For example, for hydrogen-like atoms, that is those atoms which have one electron in the valence shell, those are treated as hydrogen-like atoms. And for them, Vr, which is a Coulombic term, this is a potential, Coulomb potential, it is minus 1 by 4 pi epsilon naught Ze by r, simple potential between two charges, positive and negative. That's attractive potential, so the minus sign comes here. And so dv by dr of r, it is 1 by 4 pi epsilon naught is Ze by r square. Okay, so if you put up this value in this equation here, now what we will write? We can write then delta E Ls is equal to Ze square H square divided by 4 pi epsilon naught. This, there is then another again term 16 pi square m square c square, this term. Okay, and I will turn the bracket here off, then j into j plus 1 minus l into l plus 1 minus s into s plus 1, and then I can write 1 by r cube, but it is average value. Have you calculated this value somewhere? I think you have done it. किया है कहीं पर?
Yes, sir.
I think you किया होगा when you solved the hydrogen atom. And you took the,
yes, sir.
yeah, you took the average. You might have done like this, NL 1 by R cube NL.
1 by r cube.
Okay, so you might
Yes,
you
sir.
have also done NL 1 by R 4 NL. is a problem in the Zetly. It is given there. I will give you the page number and all that. I have written it somewhere. Let me check. Let me see if it is here. It is not written here. I will. So it might be here. No problem. Here it is. So this is the spin orbital interaction term, dV by dr. Yeah. And here it is. You can also do it from this book. This is Zetly actually. So you can also do it from here. It has used the Bryant-Cut notations, and you can also do it. The result is same. Let me see the value. Yeah, here it is 1 by r cube, and it's in the chapter 6 of this book. 1 by r cube, yes. S0 perturbation. I have done it recently. I saw it in the morning. Okay, I will send you it separately. Let's leave it here. And this 1 by r cube of average value, 1 by r cube, it's averaged over the whole radius of the hydrogen atom, orbit of that hydrogen atom, and from the radial function. And when you saw the genetic function representation it is also called a genetic function representation, but you can directly solve it by using that Cramer's equation is there. I think that you must have done it, Cramer's equation. And from that, when you solve 1 by r cube average value, it is z cube divided by a naught cube n cube L 1 by 2 into L plus 1. It is provided that L must be greater than 0. Yeah, for this case. So this is average value of 1 by r cube. I can write, and stop this bar, I will write it like this. So this is the value where a naught is the Bohr radius, Bohr orbit. Is the radius of the smallest Bohr orbit actually of the hydrogen atom, and a naught has the value. It is 4 pi epsilon naught h square by 4 pi square m e square. This is the a naught, Bohr orbit radius, Bohr radius. This. And this all has been calculated for the first orbit where psi is taken as wave function e raised to power minus 2r by a naught, I think. This expectation value is the expectation value actually of an r position called this radial function, and psi for this has been taken like this, e raised to power minus 2r by a naught for the first orbit of the hydrogen atom. Now using these values, this and this in our equation here in this equation, just see this equation, and we will use the value instead of this 1 by r cube here. So instead of this 1 by r cube, we will use this value. And what we will obtain, we will write then delta E ls is equal to z e square h square divided by 4 pi epsilon naught, it is 16 pi square c square into, here it is again z cube, it is a naught cube n cube L into L plus 1 by 2. Don't worry about the expression, because if you understand the above steps, it will be easy for you. I will write this factor here, j into j plus 1 into r minus L into, that is here. Just see this. Here is the z cube of 1 by r cube. This is this term. From this, then we have not used the value of a naught cube, a naught, and if you make some substitutions, like if I put ME4 divided by 8, you might have seen it in the last class, earlier classes. It is nothing but Rydberg constant for infinitely heavy nucleus, this factor. And we will make another substitution, E square by 2 epsilon naught Hc, it will be alpha. To just simplify the above expression, because these are constants actually. These are constants you directly need to put up the values for a particular atom here. Okay, because if you know the atom, you know the this M, okay, mass, and it's mass of electrons, so this is constant for everyone then. And if you use, this is the Rydberg constant, and this is called fine structure constant. This is called fine structure constant, E square by 2 epsilon naught Hc. So using these values in the above expression, we can write delta E L comma S is equal to R infinity alpha square Z4 Hc divided by 2 N cube L into L plus 1 by 2, where at the there are some few more steps only remaining. Just have a patience. This is the term J into J plus 1 minus L into L plus 1 minus S into S plus 1. So this is the term. Okay. Now, this is the energy of an electron, which is under the influence of interaction between its orbital motion and the spin motion, because we have converted that relative frame to the normal frame here. Just remember that. We have converted that, we have made a transformation from relativistic frame to the normal frame, and we are then in the normal frame of reference, why we don't take any relative motion. And you can, because of this interaction, because it is a perturbation actually, it's because of the perturbation of some another field. So because of this perturbation, and there's a shift in the energy levels, the energy levels will change. That will be called as, okay, so what I am saying is that this equation is representing actually the energy, or the energy of an electron, energy of an orbiting electron, which is under the influence of the perturbation field, that is that magnetic field, which was because of the nucleus. But the equation is in the normal frame of reference. We don't have here the magnetic field because of that nucleus, but what we have treated is the effect of that magnetic field on the energy of that electron. So directly it is not involved here, but we have only calculated the energy which is stored in the electron. So this is the interaction energy actually. So there's a shift actually called, that's called term shift. Term is defined as E by Hc. This is the term T. It refers to the value of an energy level actually. It's the energy value. Hc is there to make it a normalize the equation and to make the dimensions of the equation equal. And when we divide E by Hc, it becomes term. So for this case here, there will be delta TLS, it should be delta ELS, and it is minus actually divided by Hc. We have done this actually in the one of the classes. Yes. So using this expression in above, it gives us term shift of minus alpha. This is infinity, and that is alpha, that is separate. L plus 1 into SS plus 1 minus S into S plus 1. The final expression is here. You can remember this expression, or you can remember the term shift expression. You can remember this term expression, this one. Okay. And now, if we solve it for hydrogen atom, if you solve this expression, find structure expression for hydrogen atom. If you solve the fine structure fine structure term for hydrogen atom, can you hear me?
Sir.
Okay. Now, for hydrogen atom, we have one electron, a hydrogen-like atoms, that is S is 1 by 2, and J is L plus minus S, which is equal to plus minus 1 by 2. L is 0. Simply, I will take it L plus minus 1 by 2. Let it be. We will not treat it as L is 0. If you make this substitution in the above equation, this J into J plus 1 minus L into L plus 1 minus S into S plus 1. And it will be equal to L simply. So this is when we treat J equal to L plus half, in this case. When J is L minus half, it becomes minus into L plus 1 when J is equal to L minus half. So use these values, J equal to L plus half here, and J equal to L minus half in this equation. This becomes L for L plus half, and this becomes minus L plus 1 for L minus half. Simply, this is the substitution of J. And delta TLS for J equal to L plus half, that I write it dash for L plus half. Okay, this is for L plus half. It is equal to R infinity alpha square Z4 divided by 2n cube. There is minus L into L. This L. For L minus half, delta T I will write double dash L comma S. This is J equal to L plus half. This is J equal to L minus half. Okay. And this will be equal to R infinity alpha square Z4 divided by 2n cube L plus 1 by 2 into L plus 1. So, and here it is again L plus 1 because of that J into J plus 1 minus that factor. Now, if you see these two terms, this is L, this is L plus 1. So if it is L, the next will be L plus 1. So what does that mean? That means the spin orbit interaction causes each term, that is energy level, of a given L to split into two terms or different J. For J equal to L plus half and J equal to L minus half are two J different values. And the spin orbit interaction, it shifts that J, one above and one below, that is L and L plus 1. So this is the difference. So this is what the spin orbit interaction term actually do. It do make a shift, it splits actually L into two terms. One displaced upwards and the other downwards. And if you want to find that difference, how much the shift is, differences between two terms, two energy levels. Term means energy level. Then we will write delta T is delta T LS double dash minus delta T LS dash. So the term, this difference between two dash levels, that is L and L plus 1, this difference will be delta T double dash minus delta T dash, and it is equal to R infinity alpha square Z4 divided by 2n cube L into L plus half L plus 1, there is 2L plus 1. So this 2L plus 1 is equal to 2 into L plus half. This 2 into L plus half and L plus 1 is same as this. So this and this will cancel. You just take 2 common. And that will become 2 into L plus 1 by 2. So it is equal to R infinity alpha square Z4 divided by n cube into L plus 1. If you put up the value of R infinity, you know that it is 1.097 10 to the power minus 7 per meter. And alpha, if you calculate, it is 1 by 137. This is a fine structure constant. This. You just put up the values. This while we have done the substitutions actually. Here, electron, this is the permittivity, this is the Planck's constant, velocity of the electron, that if you put up these values, and you will find this is equal to 1 by 137. And we get delta T is equal to 584 into Z4 divided by n cube L into L plus 1 per meter. This is the shift actually, so it is in distance units. Centimeter, and multiplied by, divided by 100. So this is the spin orbit interaction for the hydrogen-like atoms. And if you see that this delta T is directly proportional to Z4. So it is large for heavier nucleus. And it is inversely proportional to n cube L. Okay, so it inversely depends on L and N, but it increases as we increase the Z. Okay, then we will, this is it for today, I think.